Hi everybody. I think tonight we shouldn't have the technical glitches. I did a little work with the folks at Blackboard and we'll see how it goes. So I'm going to attempt now to share my my OLI here. Let's see here. All right, can everybody see my OLI screen? Good. That makes me happy. All right. This part of the screen is supposed to disappear. There we go. Okay. All right, so let's talk about Module 4. And then you guys can ask any questions you might have, and then we can talk about the test a little bit. So Module 4 is very related, strongly related to Module 3 in that it's still about scatter plots. It's still about regression. It's just about a different type of regression. It's about a regression called exponential regression, or exponential growth or decay, compared to linear regression, which could also be linear growth or linear decay, as we did in Module 3. So we start off with an example, and I'm not going to go through the example, but what you need to pay attention to in this is if we try to model the data with a line, if we do a regression line, you can see the line. You may not have noticed it with just a scatter plot by itself, but once you plot a line on the graph, you can see pretty clearly that the points would be better modeled with a curve. So let's see if we scroll down a little bit further. This is the regression, the graph at the bottom of your screen now. That's the residual plot. And you can see there is a pattern. They're above the line, then below the line, then above the line again. So that's something we don't want to see in a residual plot. That tells us that a curve would have been better. And then we do an exponential curve, and that curve follows the points quite well. And now it says the predicted number of equal pairs is 121 times 1.083 raised to the power t. Now, you need to know what your variables are. So t, I can see here, if 1963 is t equals 13, then t is basically the number of years after 1950. And the equation didn't do a very good job. It predicted a negative value there. The linear model, sorry, it predicted a negative value. You can't have negative number of equals. But the exponential model was considerably closer. The exponential model gave us 341. Just as an aside, why don't we real quick look at how you use the calculator to do a calculation like that one. Yep. Yes. Okay. So if I bring up my calculator now, there we go. Let's take this large screen off. All right. So I realized I've been playing around with this, and you can't. It's impossible for you to see what buttons I'm pointing at. So I'll do the best I can. But we have 1, 21. So it's typing the number, and then where it says what times 1.083. You can just type parentheses, or you can do times whatever works for you. But you can even leave out the parentheses and just type times 1.083, and then you use the button just above the divided by key, which is sometimes called a caret. Looks like that. It's directly above your divided by key. That's your power, and then you type 13, and you hit equals, and there you get your 341. Since you have to have mating pairs, you can't have fractional or decimal numbers, so you would round to a whole number here. So we have, that's how you would use your calculator to input data for that. All right. All right. So let's join this. And let's go on to the next page. All right. Okay. So what is this? What do these numbers mean? So in our linear regression, we have a slope and we have a y-intercept, and those tell us two different things. The y-intercept, and this is why I like to put it first, the y-intercept tells us sort of the starting value in some situations. It's the value of y when x is 0. Well, that is also the constant number in this equation. So if we have, here's our equation right here, all right, and you see the number that's not associated with the variable is this 121. And what that means is that's sort of the predicted number of eagle pairs in year 0, or in 1950. Now, in this particular example, that's probably not going to be a very good prediction. Let's go back to the graph for a second so we can see why that's not a very good prediction, or why it may not. It might be, but why we shouldn't count on it being a very good prediction. I'll go back to the previous page. There we go. All right, let's go back and look at the scatter plot with the graph drawn in there. All right, I'm actually going to take a guess. Why do you think I shouldn't really count on the prediction this model makes for 1950? Anyone want to take a stab at that? Why is that 121 number not very... So I can interpret it. It's the predicted number of eagle pairs in 1950, but it's probably not going to give me a very... Well, I shouldn't count on it giving me a very good, that being a very accurate result. So I want one of you guys thinking about, and you can answer this question based on Module 3 knowledge. You don't need anything from Module 4 to answer this question. Because the number of not the number of eagle pairs is not in the range, but that's the right idea. Nope. Look at the first dot on the lower left there. What year is that, roughly? You can probably figure it out because each line on the x-axis is years, the y-axis is equal pairs. So every dash on the x-axis, the t-line is 2. So you should be able to figure out what year the first dot represents. What year is that first dot? Nope, not 1950. Nope. Okay, so let's scroll down. Try again. Let me do this. Let me see if I can get... Yes, 1963, in fact, because it says 1963 is t equals 13. Oh, we lost Isan. So it says 1963 is t equals 13. So the first year for the graph is 1963. So it's not that it's not that that the number of equal pairs is outside the range. When we're talking about predictions, we're plugging in x values in this case, or in this case t, years. So it's actually the number of years 0, 1950, which year 0 is 1950. That's not within the range of the years that were used to create the models. It looks like the earliest year that we have data is 1963. And it looks like the last year, it's hard to tell where that last dot right up here is, but maybe close to 50, so about about 2000. So we have data from 1963 to about 2000. I might even have said that up at the very top. Oh look, there's all the data right there. You can see then that you wouldn't want to make predictions much before 1963 or much after 2000 based on this model, because those are the years used to create the model. So, but that is what the 121, if you were forced to make an interpretation of the 121, that's what the 121 tells you. Okay? Now, all right, let's go back here. I came away from the first couple of sections with a couple of big important ideas, one of which is that if it's outside the time, be careful. Yes, absolutely. So in this case, 0, a t of 0 is well below the smallest t used to create the model. So saying that I would predict there's 121 equal mating pairs in 1950, that's probably not a very good interpretation. I'm even curious to see if they actually say that in here somewhere. If they actually warn that. Let's see here. It doesn't really look that on that. Interesting. No. I think they should have said something about that, about interpreting that 121, because it is dangerous. That's far enough below the 1963, or 1950s, enough before 1963, that it would be dangerous to use that. All right. Now, as far as the 1.083, I'm not going to go into all the details here, but if you multiply, well, first of all, exponents get really messy when you work with negative numbers, because as you go odd, even, they bounce back and forth between positive and negative. And then if you have fractional exponents, which is perfectly legal to have an exponent of, say, 1/2, that causes problems with negative numbers. Now I'm going to ask you another question. This would be an intermediate algebra question. So we'll see. I don't know how much you remember your intermediate algebra. If the exponent is 1/2, I assume everyone knows what an exponent of 2 means. It means so like here, right here, if you see this 1.083 to the 2, that means squared, and that means 1.083 times 1.083. But do you know what, if instead of a 2 there, it was a 1/2, what that would mean? Does anyone know what that would mean? Gypsy has no idea. So exponents don't have to be whole numbers. They don't have to be integers. Tiffany? Isan. I hope you can hear us, Isan. I don't know. I hope your speakers are working. Zero equals 1. How does 0 equal 1? The 0 power, something to the 0 power equals 1. That's true. All right. Yes. All right. So the 1/2 power, that would be a negative. Isan, a negative 1 over 1.083. that would be the -1 power. Negative powers mean to take the reciprocal of whatever you would have. So like if the power was -2, you would do 1 over 1.083 times 1.083. Once you did your 1.083 times 1.083, you would do 1 over that. And that would, in theory, tell you the number of the predicted number of pairs in 1948, because that -2 would mean 1948. Poor Isan is having trouble staying with us. All right, so 1/2 power, what it actually means is square root. And that's why you would have trouble with negatives. So all that's to say that this number right here in the model, let's go back up to the model here, this number right here, it needs to be positive, because you run into issues if you work with fractional powers and that sort of thing, and it bounces back and forth. You don't really get a meaningful value if that's positive. The other thing is you don't want it to be exactly equal to 1. Because 1, get ready on your chats here, 1 to any power is, yes, it's 1. That's right. 1 to any power is 1. It doesn't matter. So if I stuck a 1 where that 1.083 is, I might as well just say the predicted number of equal pairs is 121, no matter what year it is. So that's not it would just be a horizontal line. So that wouldn't be very interesting either. So basically, that number is always going to be positive, and it's never going to be 1. Okay? Well, relative to 1, if you multiply 121 by a number, and your answer is bigger than 121, what do you know about the number you multiplied by the 121? So you start with 121 and you multiply it by something, and the answer is now bigger than 121. It's bigger than 1.5. It could be, but it doesn't have to be quite that big. Yes, bigger than 1. Yeah, I mean, even if you look down here at this line right here, when I did 121 times 1.083 to the first, which is just times 1.083, I get a bigger number. So basically, if you multiply by something bigger than 1, you get an answer that is bigger than you started with. If you multiply by a number that's smaller than 1, like say 0.5, which is a half, you end up with a number smaller than you started with. So basically, this number that's raised to the power, if it's bigger than 1, it's growth. If it's smaller than 1, it's decay. It's always going to be positive. It's never going to be equal to 1. So bigger than 1, growth. Smaller than 1, decay. So this is growth because it's bigger than 1. The number of equal pairs is growing each year by how much? Okay. So I might go into my whiteboard here because this will be easier to write to show you. But this is the way, I'm going to show you the way that percentages should have been taught when you were in middle school. But they probably weren't. So once this comes up, it's loading up quite slowly. I might be taxing my system a little bit here. Yeah, I don't like the whiteboard on this software, but where are you? Oh, there it is. Okay, good. Okay, so like I said, this is the way I think that it should have been, that you should have learned how to do percentages. Okay, so the traditional way is let's say you have, let's say you're investing money, okay, and let's say it goes up. You're gonna invest and you're gonna get 8% a year. So it's a reasonably good investment. Okay. Well, you may be familiar with the traditional way of increasing an amount of money by, or anything, by 8%. So let's say we start with $500. You invest $500. So it's a small investment. It may not seem small right now. Hopefully someday a $500 investment won't seem like very much. All right. So if you say that's going to increase by 8%, well, what you would do is, most people, what they do is they then multiply that by 0.08, and then they add it back to the amount they started with. And so your next line, 8% of $500 is $40. So you make $40 in your first year, plus 500, and that equals $540. So after 1 year, you would have $540. Okay, so great. Now what about the next year? Well, the next year, you're going to take your $540 and you're going to multiply that by 0.08, and you're going to add that to your $540 that you started with at the beginning of the year. And okay, now it's getting a little bit trickier. Well, 5% of 500 was 40. 8 times 4, 3. So 8% of 40 is $3.20. So that would be, let's see, this would be $43.20. Well, it makes sense that I make a little more now. Plus my $540, that equals $583.20. Okay, all well and good, not that hard. I mean, you would just type this into your calculator. You wouldn't actually do this by hand like I'm doing it here. But suppose I said, well, how much money are you going to have in 20 years? Well, this would be tedious. So now I've got after 1 year, 2 years, and I don't really want to do that 20 times. That isn't royal. Well, let's say after some number of years I have X dollars. Let's do that. Well, how will I know after I have 1 year later? Well, I would take my X and multiply it by 0.08, and then I would add that to the X dollars I started with at the end of the year, and that would tell me how much I have at the end of the year, right? Well, let's do a little bit of algebra. Let's rewrite this as 0.08x plus, I never do this, but I'm going to do it here to make it easier to see, plus 1x. What is 0.08x plus 1x? You can use your microphone or you can chat it in. What's 0.08x plus 1x? Oh, nobody's chatting. Here comes Gypsy. Or Isan. Isan has it. 1.08x. If you think about it, if I had done easier numbers, you would have gotten it immediately. I think if I'd have said what's 3x plus 2x, most of you hopefully would have remembered that you just do 3 and 2, and that's 5x. Well, this is the same thing. You just add the numbers in front. You add the 0.08 and the 1, and you get 1.08x. So if you start with x at the beginning of the year, you end up with 1.08x at the end. Well, the next year, you would just multiply by 1.08 again. And the next year, you would multiply by 1.08 again. Well, then at the end of 20 years, you would have 1.08 to the 20th times x, because each year you would have multiplied by 1.08. And if you remember, that's exponents are short for repeated multiplication. So if I had started with 500, I would take my here, and I would do 500 times 1.08, and then use that caret button for the power to the 20th. And after 20, wow, that would be pretty nice. After 20 years, I would have more than quadrupled my money to $2,330.48 if we were going all the way out to the penny. All right, but the nice thing is now I can do this for any amount of money, and I don't have to do this whole process of repeated. All right, so well, that's all well and good. What if it was a different percentage? Well, what part of the 1.08 here comes from the percent? Well, the 0.08 from the 8%. So in general, what you can think of is the 1 is 100% and the 8 is 8%. So I did 100% plus 8% equals 108%. It works the same way, so this is growth. It works the same way in reverse for decay. What if I had an 8% decay? Well, then I would just do 100%. Instead of plus 8%, I would just do minus 8%, and I would get 92%. And for the arithmetic for each of these, you change them into decimals by moving your decimal 2 places to the left or dividing by 100. So the 108 would change to 1.08, and the 92% would change to 0.92. Okay? All right. So basically, all you have to do is take the difference of your number under the exponent and 1, and then change that to a percentage, and that will be your percentage growth or decay. Okay, so that was a long-winded explanation on how to do percents, but let's go back and apply it here. Here's our 1.083. Well, if I subtract off the 1, that's 0.083. And what that tells me is that on average, my eagle pairs are increasing by about 8.3% per year. Because I would take that 1, subtract that 1, and I get 0.083, and then I would move the decimal 2 places, and that would put it right between the 8 and the 3. And so that's what the 121 tells me how much I started with, and the 1.083 tells me how fast I'm growing or decaying. We call that the growth case. If it was less than 1, we would call it the decay factor. But it tells me how fast it's growing, and it tells me it's growing at about 8.3% per year. So that's what these two numbers. And it's just like the y-intercept and the slope on the line. The y-intercept tells me where I started, and the slope tells me how fast I'm going up or down, just in a linear fashion instead of an exponential fashion. So, and like I said, I wish that this, what you're seeing here, I wish this was the way that you were taught to do percentages. Maybe not when you very, very first learned, but certainly in high school. This would be a much, much easier way for students to do percentages quickly rather than do this whole tedious task up here at the top, to rather just do this task down here at the bottom. But I do this with my college algebra class, and very few of them have ever learned how to do percentages that way. All right, so let's see here. As it says here, so that number is the growth factor in this case, and then we talked about how to change it into a percentage increase. They go through that here. And so we go down here, and as I said, I can't make this any bigger. But this says 7.2%. It's growing. So I would do 100 plus 7.2%, and that's 107.2, and then move the decimal 2 places. And that would tell me that this would be my best answer right here. I would put that. And it would say, good job. All right. So I'll go on to the next page. Oh, and real quick, I'm going to go backwards again 1 page. At this rate, we'll never get through Module 4, and I was promising it would be faster. We're actually already through a big part of the meat of this module. Going back here, I would strongly recommend, after you watch the video on doing exponential regression, put the data from this table, the years and the eagle pairs, into your calculator and do the exponential regression, and make sure that you get, oh, where are we? Oh, come on now. Make sure you get this equation, okay? That's a good practice. When you have the data and you have the equation, and you're trying to practice a skill on the calculator, make sure that you can do it. All right? All right, so let's go on to page 3 in this module. Any questions so far? Is this video going to be available later tonight? I'll go home when I have a better one. Yes, I will. As soon as we finish. I am recording tonight. As soon as we finish, I will. Yeah, I've seen that you've had trouble and you've dropped out some. I will post it to Piazza as soon as we finish. So if you're not able to stay with us, that's fine. I can understand if you don't have a very strong connection. But yeah, as soon as we're done tonight, I will post the link to Piazza. All right, so here's kind of a summary of an exponential model. All right, good night, son. Have a good night. So y equals c times p to the x. And actually, this is the general form of any exponential model, not just growth. So c is the initial value, the y value in x is equal to 0, or the y-intercept. And b is the growth factor if it's greater than 1. If it's between 0 and 1, it's the decay factor, because multiplying by a number smaller than 0 would cause it to drop down. And then they compare that to the linear model, just like I was just mentioning. Something else I like to mention here is, this is from a standpoint, this is not something that you have to know at all, but it's kind of interesting that you can make a very easy one-to-one comparison of the numbers between 0 and 1 and the numbers from 1 to infinity. In other words, I can pair exactly, I can make a unique pairing of every number between 0 and 1 to a different number between 1 and infinity, and the other way around. So in some sense, you could say there's the exact same, the space from 0 to 1 has the exact same amount of numbers as the space from 1 to infinity. Of course, the answer is they both have an infinite number of values. And the way you do that is just take the reciprocal. So it's easiest to think of, if you think of your whole numbers, 2 to 1/2, 3 to 1/4, 3 to 1/3, 4 to 1/4, 5 to 1/5, and so on. So you might think, well, there's so many more numbers that represent growth than decay, because growth is 1 to infinity and decay is 0 to 1. But really, if you just take the reciprocal, each number is paired from 1 to infinity is paired to a number from 0 to 1. So it's just kind of a little interesting mathematical tidbit. Or perhaps you don't think it's so mathematical. Or so interesting, I guess. Oh, one of these days I am going to put the CDF player on my computer. But here's another chance with the data in this table. I can't paste it. But with the data in this table, to practice doing an exponential regression on your calculator. So I'll just, and it allows you to play around with the C and D to find a decent exponential model. But of course, you can also just plug the data into your calculator and do. Let's go to the calculator. I'm not going to do an example right now, but if we go Stat and Calc, exponential regression is a little ways down. It looks like maybe it's number 9. Nope, it's letter 0. It's number 0, which is the 10th thing down. So there's your exponential regression. That's how you would get the equation for these. Is 0. And as long as you kept your explanatory variable in list 1 and your response in list 2, you don't necessarily have to put the list, but it's not a bad habit to be in. All right, let's see what we got here. I'm guessing that one of the main things we have left is to look at a decay model, and we'll do that. All right, winter run Chinook salmon on the Sacramento River. All right, so we're East Coasters, so we don't think about salmon very much, but salmon are fish that live in the salt water, but they breed in fresh water, so they always have to swim upriver to breed at certain times of year. And it's interesting that we got a question here. While you flip, I like module. Wait, I'm confused. While you flip through, but I liked module 4 more than module 3. I'm not understanding what you're saying there. It made module 4 made more sense, just the way it's written. You mean? I assume that's what you're saying? Okay. All right. Well, good. Yeah, that's good to know for sure. All right. So so here we've got our salmon, and I've never seen it, but apparently I've seen a friend of mine has taken pictures of it. Almost all the rivers on the west coast have dams, and they basically build these steps for the salmon to go up, or these channels for the salmon to go up to get past the dams, and it's quite. I've seen pictures of it, and it's quite amazing to see all of these salmon going upriver. But anyways, so this is talking about the decline of salmon. So now we're going to get a chance to see exponential decay, and there's a picture of the graph. It's pretty stark though. It goes down really steeply and then it's almost flat. So I'm not even sure that it's clearly nonlinear, but we'll see what the exponential graph looks in a minute. You can see here, I'm not going to click on it at the moment, but you can get the actual data if you want it, and if you want to, again, if you want to type it into your calculator, looking at the number of dots, it's quite a few, but it wouldn't be so hard to type it into your calculator. So there's calling T the number of years after 1970. So 0 is 1970, and then so 10 would be 1980, and so on. If we go back up here, let's see when they built the dam. It says they built the dam in 1967. So I don't know why it took so long for the salmon to plummet. I mean, if 1967 was when they built the dam, they stayed pretty high for a little while after that, but then somewhere right around 1980, they practically disappeared from the Sacramento River. I think I was reading just recently, just coincidentally, that there was a story about railroad tank cars and the fact that they're not very strong, and so there was some accident and there was a big chemical spill in the Sacramento River, and it might have been in the early 80s or sometime. So I'd have to go back and look and see that. Sorry, apropos of nothing. So here's our exponential curve. And it doesn't do a great job at modeling the data, but it certainly does far better than a linear graph would do. So here's the here's our model, our exponential model, and you can see our initial value, 49,304. That would be the predicted number of salmon in 1970. Obviously, that's too high. In this case, though, that number is more realistic because we actually did have a value from 1970. So now 1970 is not outside of our range. But let's take this 0.0854. Before I go any further, what I want to do is I'm going to say, okay, I can interpret that number, but how do I interpret the 0.4? Well, remember now, multiplying by that will make this smaller because it's less than 1. And what I do is I'm going to go back to this page here. Oops, I need to do that. Let's go back to my pointer. Scroll up a little bit. There we go. So I would take my that 0.0854 and I would subtract it from 1. Oh, come on, you. I do 1 minus 0.854, and that equals 0.146. You can do that on your calculator, and then you move your decimal to 2 places, and that means 14.6% decline per year in predicted salmon population on the Sacramento River. Okay, so that's what that 0.854 tells you. All right, so let's scroll down, and then they plug in some numbers. You can do that. We did an example of that. All right, and it says we're not formally going to investigate residuals for the exponential, and we're not going to develop formal techniques for assessing the fit of an exponential model. You can do a residual plot, etc. Some of the other stuff, but we're not going to worry about that too much. And in fact, remember that I mentioned that we are not going to cover that on the test either. in terms of the standard error regression. Okay, so this just goes through the same thing I just went through in terms of what do those numbers mean. Just a few more information about how to change percentages to decreases, but we already did that. Okay, so let's look at what our last page is here. So it's another CDF for now for decay instead of growth. So that's about it for Module 4. So that's what you need to know. If you're fairly comfortable with that, then you should be good as far as the quiz goes and the checkpoint goes. This is our wrap-up page with our checkpoint. There is no lab exercise on this exercise. Oh, I've completed a whopping 8% of the activities. All right. So as I mentioned before, with the extra time we have, since this was a short module, I'm going to give you guys a chance to ask a couple of questions, and then we can, if you have any, after you've exhausted your questions, we can talk a little bit about the tests that's coming up next week. Tiffany, you had a question about the quiz, I think. There was something on the quiz. Yep, I'll do my best to clarify. You should play with your microphones and see if they work any better than they used to. What do you want me to clarify, Tiffany?
Can you hear me?
I can hear you very faintly. I don't know why that is, but I can't hear you clearly. Let me try turning up the audio on my end, maybe. Okay. Use your calculator to determine the exponential regression model that describes the data. I mean, we can certainly do an example just for the data we have here. If we go back to, oh, I hear someone in the background now. You want just the equation? Oh yeah, that's all I want. If you do exponential regression, but make sure to write it as an equation. Don't write A equals this and B equals that. Write Y equals then the first number, the initial value times the B number to the X. So actually, yeah, the equation itself. You don't need to give me the R squared, just the equation. Yep. Plug your one set of data into list 1, your other set of data into list 2. Interpret the growth or decay factor. So that's basically just what I was saying. So with this example, so for example with the Eagles, no, I'm looking for an answer. So with the Eagles, I would have said the Eagle pairs are growing at approximately 8.3% per year. With the salmon, I would have said the salmon population is declining at about 14.6% per year. That's the sort of answer I'm looking for. I heard your microphone was on there for a minute again, Tiffany. But yeah, I'm getting some weird feedback. Maybe I hear you typing. Maybe that's what I heard. I use 1.5 as an input into your regression equation to interpret the result. Is this the number in parentheses? No, well, so no, 1.5, I mean, the A and the B, or in this case, if you see on my screen, the C and the B there on my screen, those are constants. Those don't change. The input is whatever you replace the X with. So what you need to think about is what does it mean for X to be 1.5? And once you think about what it means for X to be 1.5, then so interpret it in the context of the problem when it says interpret the result. So you have to, you know, so yeah, if we just talk about X and Y, you would say when X is 1.5, the predicted value of Y is whatever answer you get. And so you just need to change that so that it's in the context of whatever the explanatory and response variables are for the particular situation on the quiz. Hi, Amy, welcome. I don't know what you're asking. Is the X the C or the B? C and B are the numbers that your calculator gives you when you do the exponential regression, the stat, calc, and number 0. X is a variable, so X is going to change depending on what you plug in. So if it says the input, so if it says use something as an input, X is the input, and Y is the output. So C, B, and X are 3 different things. C is a constant, it's the initial value. B is a constant as the growth or the decay factor, and X can vary, and it's whatever number you plug in. Yes, so the X you're talking about is the exponent. Yes, the X is the X, and I mean, look at this picture right here. I mean, let me highlight it. Okay, this equation, X is right there. X is the exponent, yes. And an exponential model, X is the exponent. Yeah, that's what I was saying. Just like I said earlier, that X could be a half and it would mean the square root. 1.5, yeah, if you just type it, like, if I go back to my calculator, I could use 1.5 as an exponent. But basically, 1.5 is 3 over 2, if I change it to a fraction. And what that means is the 3 on top is the third power, and the 2 on the bottom means the square root. So if you took b and raised it to the third power and then took the square root, that would be the same as raising it to the 1.5. Here, let me bring up my calculator. Oh, where are you, calculator? There you are. Let's put out of here. So let's just, second enter. If I change that exponent to 1.5 right there, that's basically my predicted amount after a year and a half. So after 1 year, I would have, had what I think I said 540, and after 2 years, I think it was 583.20. Well, after a year and a half, it would be 561.18. So yep, no problem with using decimal numbers for your exponent. So, Amy, we have gone through Module 4, so if there was any questions you had in your own reviews, your own going through Module 4, you're welcome to ask them now, and I can talk about those right now, just answering a couple of questions, and then once people exhaust their questions, we'll talk briefly about the test. Although I will do more of a review next week on, well, Monday will be question and answers, and Tuesday will be, I guess, a review for people who haven't already taken the test. Yeah. Okay. Anything else before we move on? Gypsy, I see your chat box is up, but that may or may not mean you're actively typing. All right. Well, then we'll talk a little bit about about the test. The first thing that people always want to know is, I'll tell you what's not going to be on the test. And the answer is, what's not going to be on the test, as I mentioned previously, 3.3 is not on the test. And Module 4 is actually not on the test. I feel like since Module 4 is just kind of an extension of regression, that I don't necessarily feel the need to test it separately from linear regression, that the quiz we have on it this week is enough. So that it's not going to be on the test. And basically, if I don't cover something on a test, it's not going to be on the final exam either. So I'm not going to say, oh, you don't have to worry about it for test 1, but it'll pop back up on the... sorry. But honestly, linear regression is, if you've got exponential regression, you got linear regression. It's really the same. I know the quiz for linear regression was challenging because of the blood alcohol levels being basically not really going up by 1 at a time. They really kind of go up by 0.01 at a time. But if you go through the on-site notes and understand that one, and understand the example about the age versus maximum visibility distance for road signs, you're going to be, I think you're going to be pretty good. So those are sort of more typical examples. Sometimes I'll put a little bit harder question on a quiz because you're sitting at home, you have a whole week to look at it. Although I get a surprising number of emails on Monday night that are like, I can't open the quiz. To which my response is, why did you wait the entire week before you tried to open it? Are your tests set up like OLI? No, the tests are more like my quizzes. In terms of you're going to have a problem set up, and then you may have 1 or 2 or 3 or 4 or 5 prompts based on that situation. It's probably, if I was to say concept versus skill, it's probably about 2/3 conceptual and 1/3 skill. It's a more, I mean, skills, being able to do stuff on the calculator, that's not that important to me. So there's not that much you have to be on, you have to know on the calculator. What do I ask you? Let me remind you need to be able, basically, if you want the sum total of what you need to be able to do on the calculator for the test, you need to be able to find your statistics, like your mean, median, and your 5-number summary and standard deviation. You need to be able to find those, and you can get those in one fell swoop by the stat and the calc and the 1-var stats, the first choice under stat and the calculate heading. And then you need to be able to do a scatter plot. You don't have to create, I don't have a question on creating a histogram. I have a couple of histograms that you have to I have a couple of histograms that you have to interpret, but you don't actually have to create them. The one graph you have to create is a scatter plot, which is fairly straightforward. You just do, once you've set it up, you do zoom and 9 to get the graph, and then you have to be able to do a linear regression. That's pretty much it for the calculator for this test. Test 2 has a little bit more with the calculator as far as, well, I mean, just something in addition. But mainly the statistics, the scatter plot, and the linear regression are the main things you need to be able to do for this test. No, a lot of times students go into long, complicated paragraphs, but what I really wanted is just like 1 or 2 sentences. If you look at the quiz keys, and those are pretty good. I mean, we can even let's pull up a couple of the quiz keys. Where are we here? You get to see behind the curtain here. All right, so this is, I mean, this is already something you've seen. Oh, tell me if you can see the quiz, because this is in a different program. I can open it up a different way. Can you see the quiz I'm looking at right now? Yes, okay. Let me bring it back then. Well, no, sorry. It should be back now. Okay. All right. So here's the questions. I mean, look. Is this an experiment or an observational study? This is an experiment. The psychologist controlled who would study while listening to music and who would study in silence to see if it had an effect on their reading retention. That, I mean, one sentence to explain why. In letter D, it's a little longer. Since this was an experiment with random assignment to the 2 treatments, the cause and effect conclusion is justified. Actually, that first sentence would get full credit. I went into more details to help explain it to you, but and same thing in letter C. The first sentence is the answer. The second sentence is a little bit of help for people who missed that question. Let's see here, and I think letter D on number 2. Let's see. All right, the first sentence is longer than it needs to be. You could have just said no, because cause and effect conclusions are not justified based solely on an observational study. And then, of course, the reason why they're not justified is because there could be other explanatory variables that are not controlled, other lurking variables. How long are the quiz keys located? No, the quiz keys are where the original quizzes were. So if you go into the week 1 assignments and you go to quiz 2, the quiz 2 key is now there. And I need to put, I think I might still need to put in the quiz 4 key. I know I need to put in the quiz 5 key. And I'll put in the quiz 2 key, or sorry, the quiz 6 key for this week. Although, like I said, this week's material is not going to be on the test. But I will put the quiz 6 key up fairly early on. I'll try to get it up Tuesday morning, so that people have it. So yeah, if you go into Blackboard, click on the same week's assignments. I post the quiz key right with the original copy of the quiz, so that you can open both of them side by side, or so you can retry the quiz problems, that sort of thing. But that should give you an idea. I don't really want to. I mean, usually, sometimes. Didn't mean to go back here. I meant to go and look at a different quiz key. A lot of times, students who write a really long answer, they end up writing something incorrect. They like their first 3 sentences would have been a perfect answer, and then they say something that's not right, and then they lose a point. So a lot of times, it's often better to be succinct than to go into great detail. I mean. Sounds like me. Yeah. Let's take here's the quiz 2, and you can see I mean, a lot of people, in terms of what does it tell you about the situation, a lot of people went into way more detail than they really needed to. The height of the 5 bar being 5, all that specifically tells you is that the 5 adults reported eating 4 servings of fruit per day. Some people are like, well, more people ate less fruit and less people ate more fruit. And well, that height, that number 5 doesn't tell you that. All it tells you is that 5 people ate 4 servings of fruit. And then, you know, as far as how you can tell from the histogram, I mean, there's two sentences or, you know, 3 sentences. So, you know, I'm not looking for very detailed explanations. If you've written more than 2 sentences, you probably could shorten your answer. How long will the exam be? You have 2 hours. I don't believe for most people that they run into time issues. I mean, this is the same test, more or less, that I give to my on-site students who have 75 minutes to do it. Number of questions. Do you want 1, 2, 3s, or do you want me to count all the A, B's, and C's separately? Separately, okay. If I was to throw, I have to guess. I mean, I'm not. Here, in fact, this is what I'll do. I'm going to hide my screen from you. Pause sharing, and I'm going to guess it is cool. I don't have to guess because you can't see my screen right now, I hope. If you can, I'm in big fat trouble. Let's see, where am I? Okay. I'm going to have to plug in real quick here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 3, 4, 5, 6, 7, 8, 9, 30, 31 questions. How about that? All right. So that's where we are. 31. Helps know what I'm making. So 31 questions over the course of 2 hours, 4 minutes a question. That shouldn't be too bad. Hold on 1 second. Let me plug my computer in before I'm the one who drops out, and I have to plug my computer in and this, that, and the other thing. And okay. Now I'm safe. Okay. More questions. It's pretty. I would say it's relatively evenly distributed between the 3 modules that it covers, modules 1, 2, and 3. I think it doesn't cover 1 module anymore. Anybody? You mean Ray Romano? Yes, I have been told that actually. Thank you, I suppose. Anyways, so yeah, well, you can ask some of my students. Not everybody loves me, but the important people do, so that's okay. Let's see here. What was I going to look for? Oh, I was going to go into Blackboard and pull up that test review. All right, let's take my password. I'll find out in a second. Oh, I got it. So notice that there's no test there. I will post, this is right here under the test reviews. I will also post the tests after you take them. So you'll have test 1 and the key, test 2 and the key. All right, so let's look at the review tests topics. Let's pull that up. Yeah, and I do that because that is what I use basically as the test review for the final. You can have, in case you forgot this, you can have one sheet of notes front and back for the test. They will be collected after you take the test. It's my way of, I mean, obviously you can remember some of the test questions, but it's my way of keeping someone from writing down a bunch of test questions to share with people. If you want those notes back, you can come by my office, or I can scan and email them to you. I will also scan and email a graded version of your test and post an answer key online as well. So this is for the test coming up. Yes, this is test 1, topics and questions. I don't know if you were talking about the notes or talking about this document that we're looking at. The answer to both is yes, they're for test 1. All right, so and most of this is stuff that we've been doing. This page, yeah, test 1. And this is on Blackboard under the test reviews. So, you know, give a description of a statistical study, determine the research question, the type of study, the population, sample, variables, determine what the conclusion. I mean, this is exactly what you did on quiz 1. Explanatory response variables, subjects, blinding, placebo effect, control group, random assignment. You didn't do all of that, but that's all pretty well covered. Given data in a list or table, determine mean, median, rate. I mean, so it's pretty straightforward stuff. But basically, if you feel comfortable with the stuff on this list, you're going to do great on the test. So I can write up notes for test 1, topics and questions, front and back. Take those. Sure, absolutely. You can write up. I don't place any restrictions on what you put on the note sheet. You can, you know, whatever you want can go on that note sheet. So, you know, you might want to write something. Okay, I mean, like, for example, you may go in when it talks about the value of R, how that relates to the strength and direction of a linear association. You may want to go into that page in OLI that had a few different graphs with different R values. So you may want to sketch. You might, you know, sketch one and say the R of this is close. You know, sketch a small, you know, very small. Obviously, you don't want to take up a ton of space, but sketch a few scatter plots on your paper and say the R for this one would be close to 1. For this one, it would be close. It would be positive, but closer to 0, and so on. Good. Let's see here. So like this, identify, and here's your advantage for being here, and also for anybody who has listened this far into the video, which we're talking, we're well over an hour at this point. And I'll look at those questions in just a second. When it says identify examples of extrapolation and identify lurking variables, so the extrapolation thing is it could be as simple as I ask you to use an equation to predict something, but actually the x value I'm giving you to use is one that's outside the range of the data. And rather than actually answering the question as written, the actual best thing to say is the model doesn't. This value is outside the range of the data, and we shouldn't use the model for that particular x value. You don't have to plug it in or anything. You can just say, and if you want to, you can say, you can even write, haha, I know you were trying to trick us into plugging this one in, but really it would be extrapolation if we did. So one front and back page of notes. Yes, one front and back page of notes. I think it's in the How This Class Works document. That's a pretty useful document. You can go back and read that. That's in the, I think, the class info, and you'll find that the thing about the notes in there. All right. Lurking variables. You know, that's the whole idea that two things may be related. I'll give you an example. It's not the example from this test, but it's an example I've used on tests in the past. So Yes, it's going to be on paper, this one, and test 2 will be on paper too. It'll be just like the quiz, only instead of typing it on a computer, you'll be writing it on by hand. Test 3 and the final exam will be multiple choice, and those will be on the computer, although they'll still be in the testing center. So what I was going to say about the extrapolate or the lurking variables is something like, here's an example. It's similar to the one that's in OLI, but I like this example too. When a hurricane hits a coastal area, the amount of damage it causes is positively correlated, positively associated with the number of people who evacuate. In other words, the more people that evacuate in advance of a hurricane's arrival, the more damage the hurricane tends to cause. And so the question would be, what's going on? Does this mean we should tell people, instead of evacuating when there's a hurricane coming, should instead they stay in place, since more evacuees is correlated with higher damage? And I'm going to give you the chance to answer that question. What do you think the answer is there? Why is that positive correlation there? Do you think it's because people should actually stay in place? No, a stronger, yeah, there you go, that's the answer, Tiffany. A stronger storm means more people leave, and it also causes more damage. So the hidden variable is the severity of the storm. Another hidden variable might possibly be the location where the storm hits. If it hits a less populated area, there's fewer people, as well you should. If it hits a less populated area, more populated area, there's more people to evacuate and also more structures to damage. If it hits a less populated area, there are fewer people to evacuate and less damage. So yes, so there's a lurking variable there between those things, and so and that happens all the time in newspaper stories, where they will do a headline that that makes it seem like there's causation, even though they didn't actually do an experiment. So there could be something else. It's really an association between two variables rather than, or a correlation between two variables, but not necessarily a cause and effect. A very famous study was one several years ago where they, another example of this, is they did a study and they found that children, elementary age children who studied music did better in school. And so there was all these newspaper headlines, and there was this, all of a sudden there's this rush to say, well, we should, we should try to get kids to learn music because it'll help them do better in school. But this was an observational study, so again, I'll ask you what you think might have been what might have been an alternative explanation other than that studying music. So some people might argue, well, studying music helps develop your brain in a way that will help you do better in school. But what's an alternative explanation? Another lurking variable, perhaps, that is the true cause of the association. Any ideas? Well, okay, so study habits is probably not going to make someone. So this is something that would both it would be a hidden cause of both things. So certainly study habits will help someone do better in school, but they're not going to cause someone to take music lessons or to learn music. Other ideas? Well, I'll throw one out then. Oh, I missed it. Sorry. I was saying that well, I'll say that kids who study music, who learn music, this is not so in statistics we don't deal with absolutes. So this is not 100% true, but kids who study music tend to be from higher socioeconomic backgrounds. And people from higher socioeconomic backgrounds also tend to do better in school. Yes, more affluent families. So your hidden variable there, your lurking variable, the most obvious one would be socioeconomic status. So that happens, and that's one of the big takeaways that I want you to think about when you go out and I actually more think this class is even more important for the quote-unquote real world than it will be in your future careers, in terms of, you see stuff like that in the news all the time, and people want you to believe that, that this causes that, and the answer isn't always so clear-cut. So, there could be other lurking variables there. So always pay attention to that. Let's see here. I'm thinking what else to throw up there. So on that last one there, the bottom one, you can see you don't have to worry about growth and decay factor, because that's from an exponential regression. The residual, I'll remind you of what that is. The residual for a particular x value, well, an x goes with a y, and you can also plug the x into a regression equation to get a predicted y. And the residual is just the actual y value minus the predicted y value. And they did a good job of that. Again, maybe you're right, Tiffany, and it's a good reason to go into Module 4, even if I don't cover it on the test. But they compared on that very first page the actual number of mating bald eagle pairs and the predicted value from the equation, and they subtracted. They took the difference, and that's the residual. So if it's a negative residual, it means the actual value is below the predicted value, or it's sort of almost backwards thinking, but a negative residual means that there was an over-prediction by the regression line, and a positive residual means there was an under-prediction. But basically, the actual value is higher if it's positive, or lower than predicted if it's negative. So that's what a residual is. That's just a quick reminder of what a residual is. So again, if you're comfortable with the things on this list, I think you're going to be okay. First place I would go is the quizzes and their keys. That's the first thing I would look at. After I did that, I would look at I would start to look at some of the notes and the examples in my on-site notes, and the OLI checkpoints. Probably the easiest place to start is the end of module checkpoints before you go into the individual unit checkpoints. And they'll all have, you'll be able to see the answers to them now that the due date has passed for the past one. Any other questions? We may finish a little early. For tonight. By the way, Tiffany, I just saw your Piazza message. For future reference, you can't get into the webinar more than 10 minutes ahead of time. So that's why I was asking for a password. As long as you wait until within 10 minutes of the official start time, it'll let you in. So, yeah. Oh, right. Yeah. So, yeah, 8:30 to 10 on Thursdays. But next week, no Thursday webinar. It'll be a Tuesday webinar, so earlier in the week. because the Thursday webinar won't really do anybody any good after the deadline has passed for the test. So remember that also, the test, even though it's a week, but the test is Monday to Thursday. Yes, Monday is general question and answer. I don't think I'm going to do, I may try to go back through a couple of examples on Tuesday, but I'll also reserve most of the time on Tuesday I may spend 20 or 30 minutes talking on Tuesday, but I'll reserve most of the time for any last minute questions that people have. And I may just, I'll record the first part of it, and then I'll just probably stay online after that for any questions that people have. Have a good evening, everybody. Thanks for joining, and I will talk to you next week. If you have any questions in the meantime, of course, post to Piazza or send me an email.